on the screen right now, and the title of our presentation is Things You Should Know About R2 CBO. I'd like to thank the New York Local User Group for having me, and I'd like to thank you guys for attending this session. So I was feeling that maybe the title was a little presumptuous, maybe things that you should know. Maybe you don't want to know. And what I chose is not what you want to know. So how about this? This might be a little more subtle. Things I really hope you want to know about the CBO. And I've selected a few topics. Arguably, it's the most complex piece of software in the database, and so there's lots and lots and lots of topics to choose from. There's lots and lots of new features in 11G. So what I've selected is these topics, and I hope that they sit well with you guys. Talk a little bit about feedback-based optimization. You may not have heard that term, but you've probably heard of adaptive cursor sharing. How many people have heard of adaptive cursor sharing? How many people have got 11G up and running in production? Okay, good. About half the room. So adaptive cursor sharing, is probably something you've heard of, you're aware of, but it comes out of this other thing called feedback-based optimization. We'll talk about that. Direct reads for full scans. So full scans, the DBAs in the group are used to seeing DB file scattered wait events. And full scans may not give you that. So you might get direct path read wait events. And I'll talk about that. You might be thinking, that's really not CBO, and I hope you'll forgive me if I had to stick it in here. No, it's not really CBO. It's a SQL engine decision. But it's relevant, and I think you'll enjoy it. How many people here are DBAs? Great. There's some new join techniques, or a new join technique that I'll show you. Some parallel query enhancements. Null-aware anti-joins. So there's a new way to do anti-joins that are aware of null subqueries, and it's a fantastic improvement. Extended stats. Part of DBMS stats procedure. So we can now tell the optimizer about correlated columns, and statistics on functions, statistics on views. We'll take a look at that. We'll wrap up with SQL plan management. So we're trying to avoid nasty surprises in plan changes with SQL plan management. What else is new? So let's jump right in with feedback-based optimization. This might be considered a bridge between the optimizer and the SQL engine. The SQL engine is going to start automatically giving information back to the optimizer. So what's the problem? There's lots of problems, but the two main problems that this addresses is inaccurate cardinality. Plenty of reasons for inaccurate cardinality. The number of rows passed out of a step in the plan. If it's right, things are typically pretty good. The next step in the plan is correct, whether the hash join or nested return is based on that cardinality. We have to see if this will get us better estimates. The other problem we've addressed here is bind variables. Bind variables, the problem is we don't know the value until runtime. We've seen bind variable peaking and dynamic sampling and various solutions. We'll see how this solution fits in. Of course, the bind variable value can change at runtime. And even with peaking, bind variable peaking, we haven't solved the problem. So there's feedback-based optimization hopefully gets us a step closer to solving the problem. So the solutions, as I mentioned, weren't perfect, weren't even near perfect. Bind variable peaking, when it hard parsed the query, it peaked at the value, and it optimized the plan based on the value at hard parse time. Pretty good if the values were all the same. But they're never all the same in bind variables. That's the point. So when the bind variable value changed, very often there was a need for a re-optimization for a new plan. We didn't have that ability. Now we do. Dynamic sampling, that's a pretty good solution. You can dynamic sample, you can add a dynamic sample level 4, and I'll demonstrate that to you. It's not that accurate, but it's a pretty good solution, except you have to add a hint, you've got to do it manually, you've got to alter your session. It's not automatic. So dynamic sampling is not perfect. Certainly hints to force a plan. There is a hint for selectivity, which I'll show you. These are not great solutions. We all know the problems with hints. We have to change the code. Stored outlines, not necessarily a solution for any of this, but I thought I'd mention stored outlines and SQL profiles. Stored outlines are, by the way, deprecated, and they're very, very rigid in an old technology. So if you're using stored outlines in 11G, you'll see they're starting to push you to migrating to SQL plan management. Take a better look at that as well. So plans do change, and we want to avoid bad surprises. So let's turn to 11G feedback-based optimization. So this is sort of the SQL engine passing information back to CBO at runtime automatically, and you may want to shut off. It'll work for you. Shut it. What can it return, or what does it return? Precise cardinalities. So after you run your query one time, it checks cardinality. If the cardinality is way off, it presents the cursor cache with the proper cardinality and marks the query for re-optimization. Execution statistics. Row source profiling is a new feature in 11G. It sort of is an evolutionary feature, but row source profiling counts up the number of rows in each step. And those execution statistics are passed back to the cursor cache. It provides these two new features, one which I mentioned, adaptive cursor sharing, which is a commonly heard feature, but also cardinality feedback. Let's take them each in turn. So for cardinality feedback, first let's be very clear about cardinality mis-estimates and why the cardinality can be wrong. Complex or multiple predicates are hard for the optimizer to come up with the correct cardinality. Extended statistics, which we will take a look at as part of DBMS stats, can help with this greatly. But you have to plan for them. You have to run special procedures when you know there are two columns used together in a where clause. And you have to tell the optimizer through DBMS stats that these two columns are going to be used in the where clause and they are related to each other. So that's not perfect. Functions, we often do lower and upper when we do character searches, or perhaps trunk on a date column. So all of these functions totally mess up cardinality estimates. Data skew, we should be using histograms. But histograms not perfectly often become stale fairly quickly. Missing or old stats, that should be becoming more of a thing of the past. Certainly with the auto task that runs on a nightly basis, missing and old stats shouldn't be such a big problem. Views, especially ones that are non-pushable and non-mergeable, views that will not accept a filter which you've got coded in a where clause that references the view, where the filter cannot be merged in. So it materializes the view and gives you some guess cardinality and then applies the filter to the materialized view. So these are all significant problems with respect to cardinality. And of course, one wrong estimate in your whole plan, if you have a multi-step plan, complex query, can cause the whole rest of the plan to be wrong. So let's see if this first demonstration, which I've already run, helps. I've got a simple query here. What I'm doing with the query is just selecting some aggregations from a sales table, and the sales table has got a strange name called order test cluster. Test I was doing. But what I added to the query, the notable things that I've added. First, may I mention gather plan statistics hint. This is just so I can run a specific form of DBMS exploit and not get an error. So the gather plan statistics is not really relevant to this example. It just allows me to extract the explain plan using this query. How many people are using DBMS plan display cursor commonly? So this thing has gone really far ahead, DBMS plan. And if you haven't seen the latest formulations of DBMS or the latest parameters for DBMS plan, it's really worth it to go out to it's Charles Hooper's blog. So Charles Hooper is one of my trusted resources. I'll name all of these resources at the end. He's got a great page here of all the parameters that you can feed into DBMS plan. And if you haven't seen this lately, when you're doing explain plans, really good stuff. Again, I'll mention this to Charles Hooper again at the end of this presentation, along with a bunch of other good resources. So I run this query, and the filter has a function which is very common on the date column. And let's see how it did with the cardinality estimate. Here's my explain plan. And it really did a terrible job. Absolutely awful. Off by a factor of 10, more than a factor of 10. So the estimated rows were 150,000, and when it ran it, the actual rows were a little less than 14,000. So the trunk function caused it great problems. So the first feature that feedback cardinality gives us is called Cardinality Feedback. Not well documented, by the way. So suspicious queries are monitored. And the suspicious queries are the type of queries that I just mentioned, that have things like functions or non-mergeable pushable views, complex conjunctive filters, things like this. Oracle has a list of things that are suspicious, that it may not get right. That list is not documented, and it's probably not perfect. Certainly not yet. So what it does is it compares the cardinalities after the first execution of the query. And if it finds that they're significantly different, it fixes it. Puts a note into the cursor cache, the library cache. It says the cardinality was wrong on your first try. Re-optimize this query the next time it's run. It only does this once. So it's not meant to evolve plans over time. It's not meant for situations where the data is very volatile, that perhaps, moment by moment there are tens of thousands of rows coming or going. It's not meant for that. It's only going to do this thing one time. Also, it only supports right now single table cardinalities. Join cardinalities are much more complex. Consider that if it did a hash join, the CBO, selected a hash join, and then it ran the hash join, it would feed back the correct estimate out of the hash join. But that could be completely different for a different ordered nested loops join, or a different ordered merge join. So things can change with respect to join cardinalities, but the genesis of this part of the presentation is a paper written by the Oracle Optimizer developers, and they hope to solve that problem in a future release. So let's run the query again. It's the same query. Nothing's changed in the query whatsoever. The explain plan output now shows me that the estimated rows and the actual rows are right on target. So you'll also get a note in your explain plan output that says cardinality feedback kicked in.
it automatic?
Automatic? Yes, it is. Yep. So it's automatic and enabled by default. Yes, it is.
Could you repeat the question, Greg?
The question was, is it available in release 1?
Oh, thanks.
Yep. The answer is yes.
Is the feedback persistent across reboots, or does it redo each time you restart?
Redoes it. So first execution after hard parsing does the comparison. And if you flush the shared pool, do it over again too. Okay, so it did a really nice job. So if for some reason this is causing you problems for a particular reason, not that I've discovered any yet, but somebody I'm sure will, you can turn it off, the undocumented parameters underscore optimize and use feedback. You would set that to false. Let's move on to our next feature that feedback-based optimization gives us. We're still in this conversation of the execution engine, the SQL engine, giving information back to the cost-based optimizer. It gives us a second feature related to bind variables. And we've been fighting this question about whether to use bind variable or literals since how long? I don't even know what release, but for a long time. If you use literals, you're preventing cursor reuse, causing more parsing, increasing your latching, decreasing scalability, all the bad things that come with literals. However, with literals, you tend to get a correct optimizer plan. If there's a histogram and other things. If you use bind variable, you increase cursor reuse, but you can end up with suboptimal plans. So in 9i, they introduced, and I want to mention, of course, the idea of bind variables introduced a cursor sharing parameter too. Cursor sharing equals force, cursor sharing equals exact, and everybody's made their own choice of what that parameter should be set to. So in 9i, and along with 10G, we have bind variable peaking. Bind variable peaking does it one time only at hard parse, looks at the value in the bind variables that are in the query, and it optimizes based on those current variables. Better than guessing? Definitely. Problem is bind variable values change, subsequent executions of the query may have completely different values that warrant completely different plans. Oracle's take on this at this point is, if that's the case, you should go back to using literals. So who wants to go back and change all their code? So the second new feature that feedback-based optimization gives us is adaptive cursor sharing. A query that contains a bind variable, either used in a range predicate or used in an equality predicate if there's a histogram, and only if there's a histogram. Because if it's not a histogram, things can't change, even if you change the value in the bind variable, right? If there's no histogram, there's no data skew. The selectivity of the filter is always going to be the same. So if it's an equality predicate, you've got to have a histogram. It reinforces the need, folks, you've got to be using histograms, or your optimizer's not going to optimize correctly. If you have one of these situations, or both of these situations, the query is marked bind sensitive. And bind sensitive means that a bind profile is created. And for each bind variable, a selectivity is stored in the cursor cache. And yes, so it takes up some more space in the cursor cache. Modestly so. Also, the query is monitored with row source profile. And there's two new $V views, $V SQL monitor, $V SQL plan monitor. And if you want to look under the covers, that's a good place to start, under the covers. And the query is sampled over time. And if it finds that the amount of rows that come back, total amount of rows passed through the row source, not returned from the query, but the rows that are passed through the row sources, the cumulative number of rows, changes drastically over the executions, it will then mark this as bind aware. Bind aware only happens if there's a significant difference, because there's a lot of overhead with bind aware. So we wanted to make sure that before they went into the bind aware stage, it was probably going to be worth it. They're still not 100% sure it's going to be worth it, but they want to be pretty well sure it was worth it. In bind aware, the cursor is not shared if the bind variable values are outside the selectivity range that is not stored in the bind profile. It goes through the hard parse phase. So this is way beyond peaking. This is peaking, but then let's have some information about runtime. It's all automatic too. You're not turning on something, it's enabled by default. It re-optimizes if it finds that the plan is the same. Takes the plan hash value, the lower cursor, library cache reuse, merges the plan. The plan is different, you'll find that there's a new child cursor. You can check $SQL and $SQL plan. You'll see there's a new child cursor out there in this particular case. So Oracle's now recommending cursor share is equal to force. And for all the DBAs in the room, which are most of us, you're probably cringing. And so am I. So you've got to be really careful with this decision, and you would test it inside and out before you really went this way. But, you know, the post is there, and Maria Colvin, who's a very good technician, has a blog post out there. You can check her post. And, one thing I failed to mention, because I failed to press the enter key one more time, the way the way that cardinality feedback works is not really a mystery. It's really been a technique that we've been using. If you've been using SQL profiles, you've been there for a while. So sorry to jump back on you, but you can see that hint is now in the cursor, in the query, injected by cardinality feedback. This is how cardinality feedback works. It's really simple. When it re-optimizes the query, it puts a hint in there and says what the correct cardinality is. No mysteries. This is an excerpt from the CBO trips, 10053 trips. Okay, let's see if we can make heads or tails of ACS. So what I did to try to show you how ACS works, adaptive cursor sharing, was, and I don't have the time to run the entire demo here, but I built a table, a table T, and I put some really heavily skewed values in it. And I selected where a value was very common, where the value was equal to 1, and then I selected a couple of times where the value was very uncommon, where it was 99. So I traced that, and I just wanted to show you how the trace looked, and see if this helps you lock this concept in. Again, we don't have time to do the whole rigmarole here, but this might help. So in the very first execution, the bind variable contained the value 1. And 1 was a very uncommon value, and it used an index range scan, as you can see. I asked TK Prof to give me the explain plan too, which is a little dangerous at times, as you know, because the explain plan can be wrong. But you can see the explain plan in this particular case was right. And of course, we did have a hard parse. This was the very first execution. So on the second execution of the query, and obviously this is all the excerpt of my TK Prof report, I had changed the value to a very, very common value. There were hundreds of thousands of rows that should come back. There's only 300,000 rows in the table, so it really should do a full scan. Got me? It really should do a full scan. This was the first time. But it didn't do a full scan. You can see it still did an index range scan. I ran that same query again with a very common value. And notice it changed it to a full scan. So without me doing anything, it's the same query, exact same syntax, running it over and over. All I'm doing is changing the bind variable value. And in the second execution, and this was pretty impressive. Now, the data was very, very highly skewed, and it had a histogram. But in the second execution, it changed the plan. I could tell because the third execution, the hash value changed. It changed it to a full table scan, went down to less than 2,000 logical IOs. In the previous one, it was over 2,000 logical IOs using the index. And then in the fourth and final execution, I changed the value back to 1, which was a very uncommon value in the table. And notice it went right back to the index range scan, went right back to the original plan. 178.907, yada yada. So without me doing anything except changing the value in the bind variable, it created a new cursor, or I should say child cursor, with a new plan, switched to the new plan on the third execution, and then switched back to the first plan on the fourth execution. So yeah, you're going to use some more space in your library cache. You can have a much, much more effective access path. The question is, does it do it on join conditions? No, it only does it on, I tried to force it on join conditions, and it did not. Even with extended statistics, and I've tried a bunch of different things. So it's a limited, very limited set of predicates at this point. This is 11G release 2. R2. 11.201, sorry. Yeah, I'm using the same SQL client I did last year, which probably said 10G popped up. But I still haven't fixed that. But I did notice they fixed the squeak in the door exit. But I haven't fixed my client. But this is 11.201. Let's move on to another subject. Full table scans have changed, and we'll see if it's for better or for worse. So, people in the room who are DBAs or who do performance tuning have seen DB file scatter reads for full table scans forever. Wait a minute. And this is going to change. Now for serial full scans, SQL engine can decide to do direct path reads instead of reads into the buffer cache. So what we're talking about is reads into the PGA. Yes, this is not a CBO feature, but I hope you'll excuse me sneaking it in here because I think it's fairly important. Your plan will not reveal this. It is not a CBO feature. So if you do an explain plan, or even if you do a trace, the only way you're going to find this out is by looking at the wait events. They're going to be direct path read wait events and not DB file scatter read wait events. Pros, of course, reduce latches, reduce flooding of the buffer cache with a large table. Downside is you don't necessarily have control over what is a large table. We'll talk about how to do that, but you don't have good control over that. Another downside is it's a selfish read. It's going into the PGA. You read all these blocks off the disk, and you're putting them into somebody's PGA. If another session does the same read, they have to read them off the disk. They're not in the buffer cache. So they're selfish reads. Segment level checkpoints are required. If there are a lot of dirty blocks, updated blocks in the buffer cache, they have to be flushed out. Delayed block cleanouts have to happen. It has to be a segment level checkpoint. by the way, this is one of the factors. If a certain percentage of the segment is dirty and already in the buffer cache, it won't do this. So there's a lot of variables, not all of which are documented. And also, by the way, this is another completely undocumented. The only thing I could find on it was posts that good people had put on the web and this MetaLink note, which I mentioned here. Has anybody seen documentation, formal Oracle documentation on this feature? I have not, so I'm glad I didn't miss that. So this feature can also be somewhat unpredictable. There's a lot of factors, and they're not documented as to what goes in to make a decision at runtime. So one time it might go into the buffer cache, and other sessions will benefit because they're shared reads. Other times it goes into PGA. What's large? Right now, the best guess is 5 times the value that is in your small table threshold undocumented parameter. But how undocumented can they possibly make this? So you might have a query to find out what's in your small table threshold. Let's just do a quick setup. This one fast. I asked Alex at Pythian if I could borrow his script to demo this to you guys, and I'll give you his website as well and his blog where this script is, so you can play with this if you'd like. But Alex said I could use this script. So let's see how it works. So right now my small table threshold times 5 is 3,307 points. So what I'll do is run a script. Actually, what I'll do is run Alex's function, and it will basically start loading a table. And it'll start at 3,300 blocks because I'm right in that area. And at 3,370, we should see it loads the table, 3,300 blocks worth, and it does a full table scan. And it checks whether it does a selfish read or it does an old-fashioned buffer cache read. And we should see it at 3,370 turn into selfish reads, right? Now, you can disable these. So while we're waiting for that to run, if you'll look at what I've highlighted here, you can turn this off. And I suspect, you may want to, but boy, it's a little clumsy to turn off. Huh? Either alter session and set an event, 10949 trace event, or perhaps fiddle with the small table threshold at a session level. But those are the only ways I can figure out how to turn this thing off. And I haven't seen anybody come up with anything different so far. But I suspect that some of us may want to start turning this off because we have a different notion of what a large table is, and we might have multiple sessions that want to benefit from the buffer cache out of this large table, which may not really be so large. Okay, so lots of factors. The small table threshold I've mentioned, the size of your buffer cache is a factor, number of cached blocks. If cached blocks is about half, it seems like it will turn this feature off. If the number of dirty blocks is about a quarter, it seems like it will turn this feature off. There are factors like probably ASSM, whether it's on or not, or using manual segment space management. So there's many, many factors that go into this. As I mentioned, you can disable it. Maybe an idea is to keep tables that you want to be definitely cached, put them in the old keep cache. They introduced that in Oracle 9i. DB keep cache size and DB recycle cache size, which in 10G are now separate areas from the normal buffer cache. 9i used to take space from the buffer cache. But KeyCat's really meant for small tables, so it's really not a great solution. And one last thought, compression can have an effect. I was surprised one time I enabled compression on a table, and I compressed the table, and all of a sudden it started doing, it got small enough, so it went into, no, I uncompressed it, sorry, and all of a sudden started using direct path reads. And then when I compressed it, it went to shared reads back into the buffer cache. So compression can have an effect. And just a final thought, everybody, it's completely outside the scope of this conversation, but there's advanced table compression in 11G, which means inserts and updates and deletes can get compressed as you over the life of the table. So. And exactly as I expected, just at 3370, the full table scans turned into selfish reads into the PGA. Okay, next topic I'd like to talk about is a change to nested loops. Just yet another new technique for nested loops. Just to reset traditional nested loops is a very simple process. Read a row from the driving table and scan the inner table, typically scan the inner table index. We've all seen this kind of old-fashioned nested loops, although it sort of went away and started to go away in 9i and almost all went away in 10G, which you can in fact see that this is on an 11.2 database. So the old-fashioned nested loops is not totally 100% gone. In 9i and 10G, we saw a little bit of a different nested loops. We saw a table access by index row ID above and outside the nested loop. This indicated a prefetch, batching technique, which allowed it to get a batch of row IDs and get a batch of rows from the inner table, make the nested loops more efficient. So nested loops evolved, and this started in 9i, but it didn't always crop up. In 9i, you got a lot more of these traditional nested loops looks. Okay. And what happened in 10G is they changed it all entirely again. What they do now is they take the driving table and they have an outer loop and join it to the outer table's index. If there's no outer table index, this isn't going to happen for you. And get all the row IDs, sort them, and then do reads against in an inner loop, reads against the inner table. So let's see how it looks in an explain plan, and it's really quite different. I just wanted you to be aware of it because it really does look quite a bit different. So here's the 11G version of the nested loops. Looks weird, right? That's just a join between a small and a big table using nested loops. The outer nested loops and an inner nested loops for one nested loops operation. One to join to the inner table's index, and then a second loop to go get the rows from the inner table. A couple of changes to parallel query. The most notable is what Oracle is calling auto-DOP, or automatic degree of parallelization. I think it's really a misnomer because it's really automatic parallel query. And it's a step beyond multi-user adaptive parallel query, which in a sense has been, I guess, deprecated. So with auto-DOP, Oracle decides whether or not to turn on parallel query at all, and what the DOP should be, what the degree of parallelization should be. And part of the factor, or one of the factors in that decision is the estimated elapsed time being greater than the parallel min threshold. So there's a parameter out there called parallel min time threshold, which you can take a look at. And the DOP, of course, just like multi-user adaptive parallel query, is set based on the current workload. So one time it could be 2, one time it could be 16. But perhaps more interesting is that if you turn on auto dot, you get 2 other things, 2 other byproducts come with it. One, it has an automatic, non-controllable, as far as I can tell, option to read into the buffer cache. Parallel query, full table scans, read into the PGA. They always have. I shouldn't say always have, but they have for a while. I can't say for sure, they always have. The parallel query, full table scans now have the option to read into the buffer cache. Runtime decision. So that's an interesting byproduct. And the second one is even perhaps more startling, this thing called statement queuing. If enough query processes, query slaves, are not available, it puts it in a queue and your query will wait. And there's a new wait event, parallel PQ, NQ wait event or something. It's in my speaker's notes. I've forgotten the exact name of the wait event, but you'll see it in your AWR reports or your stats pack reports. If your queries are sitting around waiting for enough parallel query processes to free up to start this thing. So, correct, and it's off by default. That's right. There is a setting. It's off by default, and there's the parameter parallel degrees equal to auto would have to be set on, or you can do so. Just on another sort of aside, not really related to auto dot, but parallel query now has automatic dynamic sampling. So Oracle will make a determination internally when and if to turn on dynamic sampling if you use parallel query, dot or otherwise. Let's take a look at extended stats. There's a couple of other enhancements, but extended stats is the one we want to focus on the most. So, 2 common issues to be tackled. Correlated columns, especially correlated columns with skew. California has the most residents. The state of Rhode Island has the fewest residents. And so if we have a query with those 2 columns in it, or a column of state in it, with a city, there should be some correlation between them. Functions have the same issue. We saw that earlier in an earlier demonstration. And we'd like to be able to collect correct statistics on both correlated or related columns and on functions. And so you can see that there's a new procedure called create extended stats, which allows us to tell Oracle that these 2 columns, and actually it could be up to 32 columns, are indeed related, have a relationship amongst themselves. If they're used, again, with a limited set of predicates, Oracle can do a better job at estimating cardinality. Let's take a look. So just to give you an idea of the structure of the table we're going to be working with, is a simple customer history table, and some first name, last name information, and then some demographic information like gender and age group, income group, and marital status. There's a function-based index on this table as well, which is the sys column, which is irrelevant for this discussion. So we have 1 million customers on our table. And how many people work and live? So the query I'm running now is how many people live and work in the financial district downtown? About 50,000. So, taking a look at the cardinality estimate, way off, factor of 10. So, in 10G, one of your weapons against this problem of bad cardinality estimate way off, was to use dynamic sampling with a level of 4, and it got better, right? It wasn't 50,000, but it certainly got better. Well, we discussed why dynamic sampling isn't the greatest solutions. So let's use the, and it's, I called it a procedure, it's actually a function. Let's use the create extended stats function. And then we'll look under the covers and see what it looks like. So what happened was Oracle added a new column to the table, and it's a virtual column. So this taps into yet again another new feature of Oracle 11g called virtual columns. And the virtual column has a system name, and it's got a function, sysop combined hash, which contains the names of the two columns that we look at extended statistics on. And of course, what that's going to do for us, that function, is allow it to calculate correct cardinality. You still have to collect statistics to populate that column with the correct cardinalities. And then, I'm not sure it'll run in time, but if I looked at the cardinality after that statistics runs, you'll find that it's pretty much right on the money at 50,000. Say again what I'm missing. Okay, so the cardinality is fixed with the extended stats. So it worked pretty good. They are indeed histograms. One would think. The question is, are they essentially histograms? In fact, they are, and they could get skewed. So you can have to update statistics reasonably often based on the volatility of your data. There's a lot of other stuff with DBMS stats, and time won't permit us to go into each one, but there's a new sampling algorithm which is much more accurate and much quicker. Even though it didn't seem a lot quicker, perhaps, on my laptop, you might have noticed that I was using the new sampling algorithm in my examples. I lost them now, but there's also, I'd like to mention, incremental partition stats. So you can collect statistics only on the new partitions. You can copy partition stats and pending statistics. There's this whole notion of, don't put in new statistics if you don't have to. So you can alter the system. So when you collect statistics, they become pending, and they're not active until you intentionally publish them. And obviously, you can test against the pending statistics before you publish them. Null-aware anti-joins. I just thought this was very good. Anti-joins are great ways to handle not-in subqueries. And this part isn't new, just a quick review. There's 3 types of anti-joins. It was affected by the undocumented parameter always anti-join, which was set to choose. And it looks like this. If you have a not-in predicate or a not-in filter, you'll see not nested loops anti. And it just probes the index on the inner table, if you will, to see if there is any matches, and returns the rows where there are obviously no matches in this case. But the problem is with nullable subqueries. And in 10G, you can see I set the features, optimizer features to 10G. If the subquery is nullable, the customer ID in my example is nullable, essentially does a Cartesian join between the 2 tables and tests every row to see if there's a match, or in this case, not a match. So you can see that the elapsed time estimate was unbelievable, and by the way, fairly accurate. So these are not really big tables, so pretty bad. So this is a problem you can easily solve by adding a where is not null filter in the subquery, but you may not have that luxury if it's a package application or something. So Oracle obviously felt it was a big enough problem to solve, and they added a new plan step called hash join or semi-join or merge join, null aware, and you'll see the NA in the subquery. Now, it doesn't fix the problem. If there are nulls, by the way, in the subquery, the query returns nothing at all. It essentially returns an incorrect result to some extent, depending on how you look at it. It doesn't solve that problem, but it solves the performance problem. Okay? So this query, as you can see, ran almost no time at all. 1 second, almost 2 seconds, from about an hour. Last up was plan management, and I found this quote somewhere about plan management, and I cannot contribute it now to somebody, but I think it was from the concepts guide, but now I can't find it. So somebody said this, and here it is. Basically, it's no surprises. We've all been burned by surprises with plan changes. Today, query worked great. Tomorrow, all my users are calling and saying the plan doesn't work. So what we want to be able to do is prevent surprises because of either updated stats or parameter changes or database upgrades or database changes. And so what we want to do, or what the database does, is to manage the plans into a repository. So in your sysaux table space, you're going to have a new repository for plans. And you're going to have a baseline if you adopt this feature. You're going to have a baseline plan or plans that are acceptable for a query. And Oracle won't use any plans but the accepted plans. Even if it when it hard parses, it finds a plan that it feels is better, that has a lower cost, it won't use it. It'll put it in the repository, but it is not accepted. It's for you as a DBA to accept it or not. So there is no surprise unless